The last thing we're going to look at in this section is what's called Le Chatelier's principle. And just like equilibrium is super important for the stuff we're going to talk about, Le Chatelier's principle has a lot of uses we're going to see. Le Chatelier was actually a person who was a miner. He was down like pulling minerals out of the earth and stuff. And he studied these systems and came up with this idea which has a lot of impact in the things we're going to do. There's a lot of things that affect equilibrium. All right, we've already seen how you can add more like reactant quotients and stuff to see, but it's more than that. You can also have changes in temperature, changes of pressure. Lots of things will affect the equilibrium position. So Le Chatelier's principle is just how a chemical reaction will adjust to a change. Here's the actual wording. If a system at equilibrium is disturbed, the system tends to shift its equilibrium position to counter the effect of the disturbance. So it's basically a way to predict how a chemical system will adjust if more reactants are added or if the temperature is cooled, stuff like that. And it's a very powerful tool. We're going to see there's a lot of uses for Le Chatelier's principle, both in the lab and also outside of the lab. If you change the actual temperature of a reaction, you can use Le Chatelier's principle, but it's important to realize that temperature will affect the value of K, all right? So temperature effects are the first thing we're going to look at here for Le Chatelier's principle. And if you change the temperature, you are actually changing the value of K, making it more or less reactant or product favored, et cetera, et cetera. Let's say we have a soft drink, all right? And the soft drink has carbon dioxide in the water. The CO2 can become liberated as a gas. Well, this reaction, which has been studied a lot by soft drink and also beer producers and stuff like that, then the way that it's written, it's an exothermic reaction. If heat is a product, that means that it's an exothermic reaction. If heat was a reactant, we would say it's an endothermic reaction. And just as a quick recall from earlier chemistry classes, if heat is a product, if it's exothermic, the sign of delta H is negative. On the other hand, if heat was a reactant, it would be endothermic and the sign of delta H is positive. So anyway, knowing all of that, let's say that we're going to decrease the temperature. At first it might seem weird here, but how you can think about it is like you're pulling the heat out of the reaction by cooling it, all right? And you can literally think about this reaction as the reaction's getting cold. And if you go outside on a cold day and you're like, brr, you'll probably go back inside and get a coat or a shawl or something to make you warmer, all right? Well, the reaction's kind of the same thing. If the reaction is cooled, you can think about it like the reaction's getting colder. And it's going to try to make more heat. So if you decrease the temperature, you're pulling the heat out of the reaction. And the reaction's going to try and make more heat. But it can only make heat if it moves to the product side. So decreasing the temperature is going to shift this reaction to the product side. You're going to see the K value actually increase if you decrease the temperature. K increases as the temperature goes down because the reaction's trying to generate more heat. It's trying to warm itself up, all right? The concentration of CO2, the moles per liter, the product side CO2, is going to be increasing. And the pressure of CO2, the CO2 on the reactant side, will be decreasing. But notice here what I did. I thought about it as if you were like a human being. You get cold, you put a coat on. You get warm, you take the coat off, right? Well, this reaction's getting cold. It's going to try and make more heat, put a coat on. It's going to shift to the side with the heat, all right? It's going to move to the product side. If you increase the temperature, now the reaction's getting too warm. And if you go outside and you're warm, you'll probably take off a coat or whatever and stuff like that to cool yourself down. Well, reactions cool themselves down by using up the heat. So in this case, if you increase the temperature, the reaction's going to try and get away from the heat. It's going to move to the reactant side, a shift to the left, trying to use up the heat. Less heat would be its way of cooling down. So notice here that if you decrease the temperature, the reaction will shift to the product side. On the other hand, if you increase the temperature, the reaction will shift to the reactant side. It's trying to get away or it's trying to get to the side of the thing you're changing. So we're changing the heat here. Decreasing the temperature is like removing heat. Increasing the temperature is like adding more heat. And the reaction's just trying to basically adjust to how you're changing it. If you can see this, you've got Le Chatelier's principle down. There is a Le Chatelier's principle guide, and I recommend you check it out for more information as well. Now, these reactions are changing the value of K, and we're going to see in a little bit, we're going to talk about Le Chatelier's principle for reactions that don't affect the value of K. Here's another example of this. Let's go back to the N2O4 equilibrium with NO2, and N2O4 is a colorless gas, while NO2 is a brown gas. Now this is an endothermic reaction, so you can think about it as heat being added, and this is the opposite of the soft drink example we saw just earlier. Anyway, if heat's being added, the delta H, the enthalpy, will be a positive number. So notice here the endothermic means positive delta H, and it also means heat's a reactant. In the last example, we had an exothermic reaction. You can think about it as heat being a product, and the delta H value would have been negative. Now, K here, products divided by reactants, NO2 squared divided by N2O4. Check out these numbers. As you go from 273 to 298, you are increasing the temperature, okay? That's what it means. 273 to 298, you're putting on a coat, all right? Or you're basically making the outside temperature better, I guess. Notice what happens for the equilibrium. You go from 0.00077 to 0.0059. We lost a zero going from 273 to 298. K is getting bigger. So we increased the temperature, we increased the heat, the reaction's trying to get away from it, it's becoming more product favored. So this is really cool. You can actually use this kind of information to make predictions as to how equilibria are going to shift. Endothermic reactions generally become more product favored as you heat them up, and the opposite, of course, if you cool them down.
In a sealed flask, we have a mixture of dinitrogen tetroxide, a colorless gas, with the brown gas, nitrogen dioxide. When we heat the flask, however, the dinitrogen tetroxide decomposes into nitrogen dioxide, creating more of the brown gas until equilibrium is reached for the higher temperature.
Notice how the flask became more brown, all right? That's because more NO2 had been formed at the warmer temperature than you had when the flask was submerged in ice, where it was more reactant favored. So literally more NO2, more brown, that's what's happening here. K is changing with temperature. The formation of ClF3 is exothermic, so again you can see heat is a product there. Cl2 plus 3F2 makes 2ClF3. So let's predict the effect of the equilibrium by raising the temperature, and there's three possibilities. No change, shift left, shift right. Okay, well we're raising the temperature, which means we're adding heat, and the reactions are basically going to try and get away from what you add. So if you're adding heat, the reaction's going to try and get away from the heat. It's going to try and make itself cool down. And notice here that it can do that by getting rid of the heat in the reaction by making more reactants. Well, shifting to the reactant side means a shift to the left. So in this reaction, we would say that if you heat it up, the reaction is going to have more reactants and fewer products. It's going to be a shift to the left. So notice that increasing the temperature on the endothermic reaction made more products. Here, increasing the temperature on this exothermic reaction made more reactants. If your system is made of gases, then you will see effects of volume and pressure as you change things around as well. Larger volume and less pressure will happen with more molecules. On the other hand, smaller volume, higher pressure will make the side with fewer molecules. So to make sense of this, let's go back here to the N2O4 NO2 example. Well, N2O4 is 1 mole, and that makes 2 moles of NO2, 2 NO2s. So more molecules would be the NO2 side, fewer molecules would be the N2O4 side. So if you start making higher pressure systems, adding like a neutral gas like helium or whatever, that's going to force the NO2s to make N2O4. Remember, every mole of gas is about 22.4 liters if it's ideal gas and standard temperature and pressure, et cetera, et cetera. So having 1 mole would take up a lot less volume than having 2 moles. And if you start pressurizing things, it's going to try and go to the smaller volume. That's kind of a neat thing. On the other hand, if you change your equilibrium to a smaller pressure or larger volume flask, i.e., if you went from a 1 liter to a 2 liter flask, for example, well, now all of a sudden there's a lot more room. So the reaction will adjust to the side with more molecules. So if you do that, go to a bigger volume, then you're going to end up with more NO2 than you would have N2O4. This only is affected by gases. It does not work for solutions. However, if you have gases, this can be really handy to make sense of the changes you see.
A sealed flask contains 3 molecules of nitrogen dioxide for every 1 of dinitrogen tetroxide, and the system is at equilibrium. If we then transfer the mixture to a flask with a smaller volume, NO2 molecules convert to N2O4 molecules, resulting in a net decrease in the number of molecules. In this way, the system compensates for the decrease in volume by a decrease in gas pressure.
In the video, that was an example of lowering the volume. It's relatively easy to transfer a gas from one flask to the other. So we went from a big volume to a small volume that forced the NO2 molecules to come together to make N2O4. And again, if you reversed it, if you put that small volume gas into a large volume, then you'd predict that more individual NO2s would form at the expense of N2O4. So it's kind of neat to see how this stuff all works out. Here's the same reaction we looked at earlier, chlorine plus fluorine making ClF3. And it says here we're decreasing the volume, okay? So we're going from like 2 liters to 1 liter, something like that. What's going to affect? Well, notice on the reactant side here, we have 1 plus 3, we have 4 moles of gas. And on the product side, we have only 2 moles of gas. So if you decrease the volume, you're pushing them together tighter, they're going to go to the side with fewer molecules. So in this case, we'd say it's going to be a shift to the right. It's going to be a shift to the product side. Decreasing that volume pushes everything together. You're going to have a higher propensity then of the smaller molecule side than you would have the more molecule side. If you add a catalyst, there's really no change in the equilibrium constant itself. However, it does affect how fast you get to equilibrium. Catalysts will affect the rates of approach to equilibrium, so it makes it happen a lot faster. Catalysts themselves won't really change the equilibrium constant K, they just change how fast it is. You're more likely to not have to worry about K versus Q if you have a catalyst, hopefully, because it'll make the process that much faster. In the production of ammonia, NH3, all right, the equilibrium constant 3.5 times 10 to the 8th at room temperature. And this is actually a pretty important reaction. Ammonia is used for a lot of agricultural uses, so fertilizer, stuff like that. It's also used for a lot of military applications, so both yays and nays. But anyway, this almost always has a catalyst in it. A lot of times, apparently, which is iron with potassium hydroxide catalyst. Usually the identity of the catalyst is kind of a deep secret because if they let it out, then competitors could make it as well. But anyway, without it, this would take a lot longer. But with the catalyst, the reaction is happening a lot faster. We're going to look at several examples here, and let's use the Haber-Frisch as an example, where we have nitrogen and hydrogen making ammonia. And notice how the N2 and H2, there's a total of 4 moles on the reactant side, and on the product side, 2 moles of ammonia, 2 moles of product. So this weird YouTube thing on the bottom here. This isn't the cool YouTube with cat videos that I'm obsessed with. Also professionally, of course, for videos like this one. But anyway, in this water YouTube, the left side is bigger than the right side. All right, and that represents like 4 moles to 2 moles, that kind of thing. If you change concentrations, moles per liter, all right, by say adding N2 or subtracting NH3, you're not changing the value of K, but you are changing the position of the equilibrium. And this crazy YouTube thing actually works pretty well to describe it. Now, YouTube is basically a factor of, the volume and gravity and stuff like that. And we can talk about taking away or adding reactants or products as we go through it. And again, remember, on the left side, that would be like the reactants, and the right side would be products. And right now, you can see that line across the line. That would be the equilibrium position. And we'll talk about how changing, adding reactants, adding products, removing reactants, removing products will affect the relative amounts of reactants and products, even though the overall equilibrium has been maintained.
When we add water to the tank on the left, the water in the tank on the right moves up, and that on the left moves down. The water moves from left to right, so we say that equilibrium shifts to the right, as it would if we added more reactants to a reversible chemical system.
In this example, the water U-tube was totally at equilibrium, and we decided to add some reactant. So maybe we added N2, maybe we added H2, whatever, okay? But the important thing here is we added a lot of water. Well, the water is going to push down on that U-tube, and in the process, the product side, the right side, goes up, and the reactant side goes down a little bit. So adding a reactant makes more product, all right? The reaction's trying to get away from what you've added by making more products. It's trying to use up the excess reactant. So if you add a reactant, the system will shift to the product side. It'll be a shift to the right, and this happens all the time. If you add something by Le Chatelier's principle, the reaction will shift to the opposite side of what you added, and that'll be important too. So adding a reactant, the reaction moves to the right, more product is made. So back to this example, chlorine and fluorine making ClF3. What's going to happen if you add chlorine? Well, chlorine is a reactant. It's going to shift to the side opposite of what we added. So in this side, if you add chlorine, you should end up with more ClF3. That's going to be a shift to the product side. And this is exactly what we saw in the video. We added a reactant. The reaction shifted to the product side, a shift to the right. Adding makes the reaction shift to the opposite side of what you add.
Removing water from the left tank causes water to move from the right tank to the left. Equilibrium shifts to the left, as it does in a reversible chemical system when we reduce the quantity of the reactants.
In this example, we removed a reactant, and you can see that as you removed a reactant, the water pushed itself over to the other side. This is what happens when you remove something. Removing a chemical from an equilibrium makes the equilibrium shift to the side you removed. So if we decided to remove N2 or decided to remove H2, a lot of the NH3 will break down and become H2 and N2 to fill it in. So removing a reactant, we have a shift to the reactant side, a shift to the left. If you remove something, the reaction shifts to the side you remove from. And that's kind of a neat thing. Equilibrium is still maintained, you're just having less product, more reactant to compensate for the reactant you removed. This reaction again. Predict the effect. Removing F2. Okay, well, we're removing a reactant. The reaction's going to shift to the side that we remove. It's going to shift to the reactant side. This is going to be a shift to the left. All right, so again, adding shifts to the opposite side. Removing shifts to the side you removed from.
Adding water to the right tank causes the water of the left tank to rise as water moves from the right tank to the left. Equilibrium in the system shifts to the left, as it would if we added product to a reversible reaction.
Remember how I said adding shifts to the opposite side? Works on the product side as well. So in this example, we're adding product water. The reaction moves to the left to try and compensate for it. If you add ammonia to a reaction, you're going to end up making more relative amounts of N2 and H2. So again, Le Chatelier's principle, you add something, reaction shifts to the opposite side of what you added. This would be a shift to the left. We added a product, it shifted to the reactant side. Same problem. I know you're getting sick of it. I am too, I guess. But anyway, here we're adding ClF3, adding a product. So adding something, the reaction shifts to the opposite side. That would be a shift to the reactant side. That's going to be a shift to the left. Adding something, it shifts to the opposite side. Removing something, it shifts to the side you removed from.
Removing water from the right tank lowers the water level of the left tank as water moves from left to right to regain an equilibrium. The equilibrium shifts to the right, as it would in a reversible chemical reaction if we subtracted product from the system.
This last one is probably the most common. Usually you want to make the product, and if you want the most product you can make, if you can remove the product while the reaction's in equilibrium, the reaction will, as this one happened, shift to the product side. Because again, you remove something, reaction shifts to the side you removed from. So removing product, the reaction will move to the product side. More reactants will be used up and more product. So if you can continuously remove product, the reaction will constantly try and make more and more and more and more product. You end up with more and more of what you're looking for. Kind of cool. So let's go back to the butane-isobutane equilibrium. We looked at this earlier. Isobutane was the 2-methylpropane, K value 2.50. It is product favored. We would expect to have more isobutane than butane. Let's say we have an equilibrium set of concentrations where the isobutane is 1.25 molar and the butane is 0.50 molar. Remember, 1.25 divided by 0.5 is 2.50, so that is an equilibrium set of conditions. But now we decide to add 1.50 molar butane, the reactant. So first of all, we're adding a reactant, okay? And it says when the system comes to equilibrium, what are the new concentrations? Well, we're adding a reactant, or adding something. The reaction's going to shift to the side, to the opposite side. So we would expect then the shift to be to the product side, i.e. more isobutane will form as we add more reactant butane. And that's kind of cool.
Butane and isobutane can interconvert to reach a dynamic equilibrium. The graph shows the equilibrium line. If we add butane to the system, the equilibrium is disturbed, and the butane reacts to form isobutane until the equilibrium is reestablished.
I like this graph. The red line is a slope of 2.5. And in some ways, an equilibrium constant is like a slope, all right? And so anytime you have an isobutane to butane mixture, which is 2.5, then you're going to be at equilibrium. So initially then, kind of down here in the bottom, that was a place where the equilibrium was. And if you look on the left, it's about 1.25, and you go straight down, it's 0.5. Well, all of a sudden now, we've added a whole bunch of butane. 1.5 plus 0.5, you end up then with a value over here that's about 2. That it's no longer at equilibrium. You're no longer at that slope of 2.5. So what's going to happen in an equilibrium system is the system will adjust to make more isobutane. You're going to end up with a higher value, again, where the isobutane to butane ratio is 2.5. So mathematically, this is kind of what happening. Below the 2.5, you can see that's where Q is less than K. And above the line right there is where you'd have Q greater than K, where you'd have too much product relative to reactant. So that's another way you can think about equilibrium if you want to. So what you can do is right away calculate Q once you've added the additional 1.50 molar butane. So again, Q and K have the same form. It's going to be iso on top and butane on the bottom. So iso is 1.25. The butane comes from two sources now, 0.50 plus 1.5. Q 0.625. Now Q is certainly less than the K of 2.5. This is not at equilibrium. Q wants to be like K. That's when the reaction is back in stasis, if you will. Q is going to have to become a bigger number. And if you're going to make a bigger number from a smaller number, there's two things you can do. You can make the numerator bigger, so you can make 1.25 a bigger part. On the other hand, you can also make the value of Q or K bigger by lowering the reactant side, lowering the denominator. So we're going to do two things here. We're going to make the top part bigger, the smaller part, the bottom part smaller. This is a shift to the right. We're making more products, more isobutane, having less reactants. So we're going to predict here that 1.25, that number is going to go up, and the total 2.0 value for butane will go down once equilibrium is established. Let's set up our good old ice table here and see if we can figure out what's going on. We only have one reactant and one product. You can see here that initially we had two sources of butane for a total of 2.0, and the isobutane was only 1.25. Now, Q is getting bigger. Q has to become bigger. That means more product, less reactant. So we're going to have a positive X for the change of product and a negative for the reactant. So at equilibrium 2 minus X, and at equilibrium the isobutane 1.25 plus X. Well, here's our X values at equilibrium. We know what the K value is, so let's throw it all together. 2.50 equals 1.25 plus X divided by 2.0 minus X. Now at this point, if your math haven't done it for a while, I'd like you to try and go from this part to an X value of 1.07. This is a good test of your math skills. I want to make sure you've got it. Yes, you can absolutely cheat if you have the solve button, but if you don't have the solve button, here's what you would do. 2.50 times, parentheses, 2 minus X equals 1.25 plus X. That's the first thing you want to do. You want to get the 2 minus X out of the denominator, and then you'll have X terms on both the left and the right. So you want to then multiply 2.50 times 2 and minus X. You would have 5 minus 2.5x equals 1.25 plus x. You then want to combine all of the x's together. You want to get x by itself, so you'll divide both sides by whatever's in front of the x. You should end up with 1.07. If you are not getting 1.07 for x here, then please reach out to me. Send me a little screenshot of what you're doing. From a camera phone is fine, and maybe I can see like how you're doing it and give you some hints for getting the right answer. None of this stuff is hard, and it's all stuff you've done before, but it's not something that most people anyway, do every day. But I want to make sure you can do it. So make sure you can go from the k expression to the x of 1.07. You don't need a quadratic or anything like that. Anyway, with a 1.07 number, then you can calculate the new value. So the butane was 0.93. That comes from 2 minus 1.07. The isobutane, 1.25 plus 1.07. That's 2.32. And again, because K was larger than 1, of 2.5, we would expect more product than reactant. We do see the isobutane is larger than the butane. That's good. Equilibrium has shifted to the right. It was at 1.25 and now it's 2.32. So adding a reactant made the products go up. Good to go. An overview of Le Chatelier's principle, I think, is kind of helpful. If you change the temperature, all right, you are changing the actual value of K, and you can change all different kinds of things. You can change pressure, volume, concentrations, anything you want. This is where we had the endothermic exothermic discussions, and you can remember that adding heat is like adding heat to the reaction, so it's going to try and cool itself off. On the other hand, if you cool it down, that's like taking away heat, and it will try and adjust. If you use a catalyst, you don't change the value of K, but you don't usually then have to worry about waiting for the reaction to get to the equilibrium position. So you don't usually need Q versus K, stuff like that. That's not for sure, but that's at least more likely. Catalysts just make reactions get to equilibrium faster, and that's usually a good thing. On the other hand, if you add or take away reactants or products, you don't change the K. Like the equilibrium water position was the same, but it will adjust to the new position. And in a nutshell, this last one, if you add something, the reaction shifts to the opposite side. If if you remove something, the reaction shifts to the side you remove from. That's kind of an overall view that works really well for Le Chatelier. It also works for temperature too. If you think about it as increasing the temperature is like adding heat, and decreasing the temperature is like removing heat.